So good morning, everyone. My name is Grigori Fursin, and just a few things about myself. So some years ago, I founded so-called non-profit tuning foundation, where we develop open source tools to help researchers automate their experiments, share them, reproduce them, and so on. And some years ago, I also created a consultancy company, dividiti in Cambridge. So basically, we help companies, we consult them how to kind of accelerate the research, use all those open source tools. And this year, I'm also reproducibility vice chair for Supercomputing 19. And again, we discussed there how we can improve reproducibility of our research and kind of how to automate it. And obviously, I'm very glad to be here because I think some of the high-level goals, basically helping researchers like to simplify their life in HPC experiments. I think it's very correlated with EasyBuild high-level kind of vision. And I think that tool which I'll present you today called Collective Knowledge, I think it can be well complementary to EasyBuild and similar tools. So obviously, I'm also here to get your feedback and to discuss things how we can automate and reproduce experiments. Just what is it all about? So I spent many years, like probably more than 10 years, working on machine learning and systems research, and recently we started looking at quantum computing. And obviously, if you look at the research, it's all booming. So there are more than 1,000 papers published every year just in machine learning. So it sounds like great. Okay, it's good. However, if you want to, like as an end user, you want to take some of those techniques published in papers and move them into practice, then you start having troubles. And basically, you need to look at many different tools out there to before you get from your idea to production. And there are, of course, many nice tools which supposedly help you in this route. And you spend your time, you learn all of them. And if you're a student, you go there, you spend like 2-3 years learning them. And by the time you're kind of ready to implement your fantastic idea, which was out there, everything changed. So your software changed, hardware changed, ideas changed, models changed. You get depressed, tired, you either quit or you search for some other tools. That's what was my path, and like path of probably many other people here. And of course, and then now we're kind of stuck with what do we do with all this complexity. And there is no universal solution for that. So just before being kind of completely depressed, I started, I tried to initiate what we call artifact evaluation at some conferences, just to start talking with the community and looking at how they share their experiments and how we as end users can reproduce them and so on. And so I organized many artifact evaluations now at different conferences in the past 5 years. And I think I overviewed about more than 100 artifacts, more than 100 papers. And what is interesting, practically none of them are automated. And if you look at all of them, actually have very similar workflows, most of them. So basically, you just get some either an archive as a zip, tar, or some container, some Jupyter notebook. Then you have some ad hoc scripts, so you have to learn how to work with them. You download some extra source codes. What if your URL changed? You're stuck. You try to get some data sets sometimes also disappear. What if I want to change and try my own different data set? Usually like start hacking all those scripts, you're lost. Of course, you have to install lots of software dependencies, and it relates to EasyBuild, which is trying to solve this. You start running compiling program. And by the time you already, usually as an evaluator, you spend like 1 or 2 weeks like hacking all this stuff. And of course, usually your program, it's good if it compiles, but then you run it, you get results which are not correlated with your paper, you start hacking it back, you realize maybe some library somewhere changes, so on. And it's total mess. So evaluating one artifact nowadays takes like a couple of weeks. And this, if you have thousands of papers, what will you do? So this is not really a good thing. However, discussing with the community, we started thinking, how can we solve it? And okay, one other thing, of course, nowadays everyone speaks that, okay, let's start using kind of virtual machine containers. They're really good tools, but they're like final tools which hide all this mess. They're not solving it. So they're extremely useful to kind of give you like a snapshot and run it somewhere. But if you're still a researcher and you want to try to change your data set, software, and so on, they're not really providing a solution for that. So at the end, I started discussing with the community how we can solve those problems. And we started thinking that what is missing here is actually a lack of APIs and common meta descriptions. So all those ad hoc steps which everyone is doing, that why not to provide some simple APIs for them, so that everyone can have the same API to perform the same task. And just very quickly, again, very high level, very kind of conceptual. So we started thinking that, okay, I would like to have some kind of tool which would allow me and everyone else like to get some repository or other repositories with components out there. I'd like to have an APIs that instead of scripts, I would be having an access to this, to see this shared artifact as kind of repository where I have APIs, modules, data, and so on. Obviously, I would like to have an API which would install software for a given program. And it doesn't, because you have like EasyBuild, you have Spec, you have Scones, you have many different tools out there. I want to have the same API for them so that I'm not changing it all the time. The same for data sets. I don't want to consider data set different from code, in fact, because you can install data as software in the same way. So I want to have the same API. So this is my first was original wish list and the list of kind of our colleagues. The same for models, packages. More importantly, if we want to move our shared workflow to some other new platform, we don't want necessarily to have like fixed software. We want to adapt our workflow to an installed software. So we don't want to have pre-installed old software. We want to really try to get really latest software out there. We want to automate compilation, trying different compilers, flags, and so on. Run code with multiple data sets. So if I can pull a new paper with a new repository with a new data, I don't want to do manual hacks. I want to immediately see all those multiple data sets out there. And with one click, I would run different data set and so on. And the last thing, I would like to automatically validate results, compare them with paper, and show discrepancies. I don't want to look at it like all our evaluators, they spend time looking at the graph, like checking what is wrong, what is not wrong manual. It's really, it's crazy. And the more papers we have and the more artifacts we have, it's not sustainable. Now, these are just maybe 5 minutes I'll spend on low-level details of this collective knowledge framework which we came up with. And I'm sorry if it's low level. I just want to give you kind of a feeling of what it does. And if something is completely unclear, I'm here to discuss it more. So again, last 4 or 5 years, I started discussing all this artifact evaluation with both universities and companies, and was thinking how we can solve those API issues. And we decided that maybe we should try to create a very simple, small program, very portable in Python, which would allow you to kind of convert all your code data mess into some kind of APIs. And it should be very simple, so that it's not like you download like thousands of dependencies and so on. Just pure APIs, like wrappers to your different code and data out there. So we created this framework, which you can see, like you can install it with this pip install CK. You need sudo because it uses binary as a front end, and again, you can run it on Windows, Linux, macOS, on different systems. And basically, it's a tiny Python library. What it does first, again, it will be some colorful things. Because I will show you what each command does, and then hopefully we'll get a feeling how it works. So basically, my first idea was that, okay, I want to start having on my machine a directory which now will have some structure, which I can afterwards maybe share through GitHub and so on, and everyone can reuse it. So let's do something. Let's create human readable APIs. So what it, sorry, I'm just trying. Oh, yeah. So first, like we started working like on front end, CK is a front end, and let's say CK add repository my paper. I'm trying to share some artifacts of my paper. What it does, whenever you install CK framework for the first time, it will create you in your home directory in CK a set of repositories, and you can then, whenever you pull other repositories from different people in the CK format, you will always pull it there. And then you just basically now create your dummy repository with just one file. Again, you can go through those steps yourself when you try to do it. It should work on your machine. And this description of this repository just have you dependencies on other repositories, because the idea is that when you start sharing APIs or a community share API, you can actually not just copy paste your modules or APIs, but you can just get a dependency from other repositories, from other paper and so on. Again, obvious ideas, but now when you just also have commands from Linux, Unix, CKLS and so on, which shows you the structure of the repositories, what you have, and later I'll show you how you can add APIs. So you can look at your repositories. Now you have a few ones like Scratchpads and your my paper repository. You can search through them. Now, adding APIs, the idea what we were talking to our users, they want to have it as simple as possible. You don't want to have like I don't know, to write your C code or something. You want from your command line to create immediately a wrapper and API for something. So let's create an API called hello. And when we want to say, let's create an API. We have a module called hello. Basically, all our APIs are shared as Python modules. And inside your Python module, you have an API called say, and we want to have from command line API called ck say hello. So what we do, we just have two commands. First command will create you a dummy ck add in my paper module hello. And you basically have a dummy here inside your my paper repository with module hello. It will create you just a simple module py automatically. And then you can add an action inside this module called say. And it will create you this just dummy function inside your Python module. And what is important is see here an input. An input is always a dictionary. There is always one dictionary which can be serializable to JSON. So it means that all our APIs can be serialized through web services. Again, later I'll show you why it's important. So now what is important that right now, you created immediately your API. You can now start using it immediately. So basically you can write say ck say hello, and you can write whatever you want here, some command lines, some parameters, and some input JSON. And what it will give you, ck will just find this module, call it, print you dump your input, and you will see this information. That's all. What is important is now you can also use it from Python, from other Pythons, or from other modules. So what it means that if I run my Python on Jupyter Notebook, I just import this ck kernel, and I can access the same function with the same command line, action say, hello, yes, cool, and so on. You do it return, and return is always a dictionary. It sounds like very simple, but this is enough to create you to let users create and share APIs very simply for anything. For now, it's very abstract, but I will show you afterwards how this converted to HPC research. And basically, just a couple of more things. So now you can also all those modules which you create, you can start creating data associated with this module, so that basically you abstract your data. So, for example, we can now create this. The last piece of information what you need to know about ck is now I want to create in my repository, my paper, with the module hello, some data dummy called world, and with some tags. And in your local directory, again in my paper repository, ck repository, under module hello, it will create you data called world with some meta JSON where you will see some tags and so on. And inside, you can actually keep it as a holder for any files which you want to share with some users. So in such case, afterwards, you can find both your modules, APIs, and data which anyone shares. So here you can search it through those tags. You can load this and get your meta information and so on. And as I said, finally, yeah, you can now say even ck say hello world with some, again, command lines, and it will again print you some meta information. Now you don't see all of it, but I hope you grasp the idea. Again, it sounds like, and so what? Why it's like kind of obvious? Seems like an obvious thing. The thing is that, sorry, I'm skipping. That now we can basically convert all our code and data into some format and start sharing it through GitHub or so on, both code and data. And in such case, we can start abstracting all our system gradually. So instead of all those steps which I showed you, we can implement those APIs for this, and then everyone can reuse those APIs. So everyone hopefully will be on the same page when you perform experiments. And also, more importantly, as soon as you have an APIs, you can really enable DevOps, because you can connect those components with Jenkins, with Travis, and so on. Now, when we created this framework, it took me about 3-4 months probably just to create this framework. Then the idea was to start talking to the community and basically start adding those APIs for our common tasks. And if you go here to those links, you will see actually already there are about hundreds of repositories shared from different partners which we have with, and also hundreds of, maybe a few hundred modules which are shared with those APIs for different tasks. So which task we started sharing? So we started working with ARM first, and they were saying some basic things, saying, you know, even like when we start, we have to run across many different operating systems. Why not to start sharing information about operating systems? It can be Linux, Windows, Android, and so on. So we created an abstraction called module operating system, and the CKN repository, you will see it, you can see it online in the GitHub. And basically the idea that if you do CKLSOS and you pull this repository, you will see now about, so ARM commits most of the stuff for Android operating system, but you will see about 100 description of different operating systems. This is just meta information. And these dictionaries are very easy to extend. So again, the point was that someone else can say, oh, I want some extra information, this JSON, I'm adding it. And you, when you pull it, you suddenly see it while keeping backwards compatibility. Then we started saying that, okay, everyone is trying to get information about platform. It's always ununified. Why not to provide API called platform? And we use the CK Detect platform API, which basically goes through different tools which are installed out there and collects information about the platform and saves them again in a unified format in JSON. And again, it has an API. The same third step which we started discussing, everyone complains about that all our workflows are not adaptable to a new software installed. So why not to, we prepared a module called soft with an action called search, so that it can actually detect a given software or data set or model on your machine and return you some different information about paths, libraries, and so on. Again, these are very conceptual. I'm just trying to give you an idea how those work. And the last thing what was missing to create adaptable workflows was these packages. So we wanted to have a unified API, again, where you can install some specific package, whatever afterwards is used, is it EasyBuild, is it Spec, is Scones, it doesn't matter. We want to have a common API which has dependencies which can install you a given package. And again, you will see about 600, 700 packages which are now shared to install not only code but also data sets and models. So anything, it doesn't matter what we install. And finally, again, I worked a lot on benchmarking and auto-tuning and so on. So our next module was called, obviously, program. And what it does is that we created a really complex workflow. We spent about a year on doing it, where you could actually compile, run programs, but you describe your software dependencies, dataset dependencies, models, and it automatically adapts to your software, to your platform. It picks up your libraries, your datasets if they're installed, the new ones if they're installed, and if not, it's automatically installed missing packages, again, through Spec, through EasyBuild, through whatever it is. And at the same time, because we now have APIs, we can record experiments with all this information flow, because we now monitor all the information flow through this API, and we can replay experiments and even find differences automatically. This is a really powerful tool. And now, so again, many companies even are using it now. So why? Because again, this API now measures that it's not just a script, it now has an API. So there was an integration with Jenkins, with Travis, and it's very easy now, because again, you have a standards API, you have JSON API. And the last just couple of things, I was very glad when I got this program workflow, because so I spent what I think 10 years working on auto-tuning, and each time I was spending probably 10% on auto-tuning or machine learning, and Kenneth probably know this task, and 90% I was spending on like, oh, my library changed, or compiler changed, or flags changing, and it was like, that was a depressing time, and I think you probably see, you know it very well. So now when we converted, when we have those workflows, I actually probably in 1 month I implemented auto-tuning, universal auto-tuning kind of module on top of this pipeline. Basically, we expose information about choices which we have, characteristics which we want to tune, and it's all automatic. I don't think about it anymore, because if someone else shares me a compiler, they share where they can expose flags and so on. I don't care about this anymore. And I was kind of crying because I spent now 1 month doing it, and we collected so much experiments in 1 month. So I spent like 5 years for my PhD of my life doing all those experiments, and 1 month now I can get all those experiments, and I'm not working on this anymore. it's kind of sad. But okay, Raspberry Pi Foundation found it very interesting, so we worked with them to actually replicate all this compiler tuning work, and we even generate fully through CK interactive articles, so you can see it here if you're interested. And as I said, there are some fun parts, some other colleagues share modules which do kind of analytics on this collected data, so they perform reduction on compiler flags or on. We're even doing software hardware auto-tuning for for machine learning models, like for image classification. And if you know AutoML, so we kind of cover all those spectrums. We can do the whole software hardware auto-tuning now. Okay. This was just to give you an idea about CK framework, and I have, I think, about 7 minutes. So I just want to quickly go through some real practical examples with our partners. So in case some of them will be interesting, you can actually go to the website and you will see links with our partners, and there you usually have shared repositories for each of the project which you have, and in case you can reuse it. And so what is an example is the first fun part which we had last year was to say, oh, okay, we have all those components and programs. Why not to start actually organizing tournaments where basically rather than you just publishing your paper and then hoping that someone in 1 month will read it, on 1 year read it, and so on, reproduce results. Why not to share papers with, for some specific task, for example, improving image classification, with those workflows. And then during reviewing those papers, we would be actually reproducing the results and publishing them on a scoreboard. And then everyone can check them and find the best solution. So the first tournament which we did at Aspelos last year, so we had a very nice, many interested colleagues in this tournament. So we said anyone can submit standard image classification using any framework which you want, on any hardware which you want. And then we want to look at the Pareto frontier in multi-dimensional space, can be accuracy, execution time, power, whatever you name, which is publish it, we place it on the scoreboard, and then we'll look at the Pareto. And it was very fun part because we get originally 8 people, 8 submissions, but 3 dropped because they got scared that if you show not good results, that people will kind of name and shame them, which was not correct, because we actually don't care, we don't care about one winner. So eventually we had 5 submissions, but again, submissions were very interesting because they were very diverse. So we had from Amazon Cloud, there was Intel submission on Cafe with the Intate inference on Amazon Cloud, from some grid of Raspberry Pi machines, which showed you that you could work faster with 5 Raspberry Pi devices. You can be fast in image classification than Tegra NVIDIA card. Again, all this is published now, and you can see that it was really fun. So we unified all those all those submissions through CK workflow. And then again, if you go through this link, you will see the live results, which were gradually adding when someone was reproducing and reviewing those results. And again, as I said, you have really lots of metrics which we started collecting. But here you can just see, I think it's, inference throughput versus accuracy on image classification. And again, models were very different from ResNet, GoogleNet, MobileNets, and so on. So obviously here you can see obviously that there is some Pareto kind of frontier. But again, these are all obvious things. I don't want to get into discussing those results because you probably worked a lot on those topics, you know it. What I want to say afterwards is we had a very interesting case, reproducibility case. So Intel actually, so they claimed a few months before this workshop, Intel published a paper where they claimed that they got about 400 FPS record number at that time on one of the Amazon instances, and some people had problems reproducing it. So they had the submission to our workshop, and we started reproducing it. And it's true that it took us a week to reproduce it because each time we're getting like first 80 FPS. Then you realize, library was not exactly the same which they were using because they had to use some specific sub-library. We change it to this version, we get like 200 FPS, still not the same. We start checking it further. It means that they use Intate inference, but the model which they used, there was a bug in the conversion, so it's still FP32, so it doesn't give you speed up. We fix it, and we get those 400 FPS, so we reproduce it. But then we share the workflow, and now all those bugs are fixed. So something what you as a paper reader, you would read and you say, oh, I don't want to read this paper anymore, I don't trust it anymore. So now this workflow was shared here. And what is really cool that 2 months later, Amazon contacted us and they said, oh, wow, you know, we got this workflow, we ran on AWS and we actually produced in 1 minute this result, it's correct. So furthermore, we tried it with different data set and it worked. And they shared it as a Docker image now inside the AWS, because now underneath this Docker, you have the CK framework where you can actually run it, test it with different data set, with different model, with different framework. So it was really a great example of how sharing your artifact in some common format will allow other people to quickly reproduce it, rather than just having thousands of papers and reading them and trying to figure out what to do with them. And they're reusable. So Amazon gave a presentation about our work a few months ago at a Raleigh conference. As a consultancy company, General Motors contacted us and they said, oh wow, we have, you know, our task, it's again public information, you can see it on YouTube, they spoke about us last year. So they said, you know, we spent years trying, well, like they build self-driving cars, obviously. So we're trying to build the software hardware stack, which has to be of this specific price. It can't be like $2,000 to put you into self-driving cars, too expensive. It has to have power budget on, I don't know, 10 watts. It has to have specific accuracy and so on. You don't have issues with not detecting pedestrians and so on. And it's really complex because we read papers, we check them, we don't know what to do. So they look at all those reproducible workflows and they start using, because it's immediate. You can get those 5, 6 workflows, you run them, you test them on different hardware, software, and so on. And it's 100 times faster to perform this validation and so on. So it really accelerates your research. And as I said, so I'm reproducibility vice chair for supercomputing. We started looking also at this year, just announced with if I'm correct, if you submit paper to supercomputing, you will have to submit artifact appendix. You still don't have to provide all the validation, but you have to describe how you, which experiments you did. And we're trying to discuss also, it's not for this year, but also how to automate it. And it's not necessarily about CK and so on. There are again many interesting tools like EasyBuild, Spark, and so on, which are out there. We're trying to connect them all and discuss. That's why I'm interested to talk to you as well, what you think about this. But one of the ideas, if you look here, for this year, we had there was a student cluster competition tournament with the very complex CSOL application, and we shared all the CK workflows with components there for this tournament. And a month later, the authors of this workflow, they actually validate the result on a different supercomputer and with different API and so on. Why? Because we had all those different packages which you can add, software detection plugins where you can adapt. And we continue discussing with them. So follow, possibly if you're interested, follow this link because we continue extending this workflow. And yesterday, guys from supercomputing, I have 3 more slides and I think I'm just like 2 minutes late. And yesterday, I'm on this committee for supercomputing. They asked me to put this slide inside all the presentations just to remind everyone that there are many open calls right now, which not everyone knows about, different like tutorials, panels, workshop, posters. So have a look at the website. This is a small advertisement because there are many deadlines coming. Just the last interesting thing, what we had just 2 days ago, 3 days ago. All those workflows, obviously now, what is a buzzword? Quantum computing. It's cool. Is it really cool? Is it really faster? Okay, we know that there is no yet a task which is faster than traditional computing, but apparently maybe in 1, 2, 3 years, quantum computing will be faster, but HPC is also moving. So you want to compare those results all the time. You want to compare systems. So several colleagues came to us from IBM, Rigetti, and the Riverline, and so on, and we started discussing why not create workflows where you can run algorithms which are usually traditional for quantum computing, cryptography, machine learning, and so on, but run them both on traditional machines and on quantum computing. Well, quantum. Either we actually ran some results, some workflows on real IBM machine, quantum machine, but also on simulator, and start sharing results. So we provided those workflows, and if you look, in Paris we had this hackathon where everyone came, ran this workflow, and they were trying to tune parameters for machine learning with Qiskit from IBM. You have online results, the winners, and if you look at them, you will see some guys were really, in 1 hour, they produced a schema with gates, if you know, with some quantum computing, which actually really get you very good accuracy on supposedly quantum computer. It's simulator, but it's an interesting result. So collaboratively, we can start searching for better solutions and share them. And I'm done because I'm actually mostly on time. So just to conclude, what I told you, kind of, either you can say, oh, it's too simple, why do we need it? Or you can say, oh, everything is solved. Neither of these. So I think we have a really interesting prototype which can show you that we can actually deal with this complexity now. And we can bring community on board so that you can share those APIs, you greatly abstract the system. But we're only really at the beginning of the journey. Why? Because now we actually need to standardize all those APIs because they're changing and so on. It's still itself, I wouldn't say a mess, but it's still, you need to standardize it. And this community has to play a role in that. Obviously, installation, documentation, sharing more components, we need to work on this. And I'm very open to collaborations or projects if someone is interested, particularly related to this automation and sharing of experiments. And if you're interested, as I said, there are a few websites where you can look at all these components which are out there already. You can reuse them. And please, if you're interested, just contact me. And I'm happy possibly for some future projects together. OK, thank you very much. And I'm mostly on time, actually. So,
any questions for Grigori?
Everyone's like, oh my god, some
strange
stuff.
Maybe I have a question.
Okay, sure.
So it looks like CK, the framework and all the models around it are all spread across multiple repositories. There's a whole bunch of
That's correct. That's
different
distributed
How do
approach.
you pull all these things together? How does that work?
Good question. Yeah. So for now, we have this website where everyone looks at it and finds the most close module which they want to use, and then they provide inside your, whenever you write your new repository, provide dependencies inside. Just say URL which one I want to pull. That's all, and then we pull it. An important thing: we don't have a cool index where someone else creates your own repository. It's all manual at the moment. So you have to tell us that you have a repository, we add it there, and it's not indexed. And this is one of the big things what we want to do next is to actually make automatic index. A bit like PEEP or other things. So when you share some module repository, you make everyone aware automatically of this existence. It's not there yet. That's why it's still must be done.
What about if I want to play around with the quantum computing workflows? There's a single repository where you can start.
Yeah, so CK minus quantum, C-tuning CK minus quantum. These are workflows which work with several simulators, so you don't need a real supercomputer. But we have some APIs. Even if you actually get an access to IBM machine or Rigetti, we have APIs. So you just need to arrange a login. You need to get tokens and so on. But it's actually pretty automated. So we did it.
Okay. Yeah.
Yeah. So there is, again, if you look at those repositories, search for quantum, and you will see it. Okay.
Any more questions?
Don't be shy. Anyway, we have 2 days, I think. So I'm happy to take your questions
around
later.
all day today and tomorrow, and at FOSDEM as well.
Yeah, that's right. So thank you.
Thank you.